All right, welcome back to the deep dive. Today we're taking a look at abstract algebra. I know that sounds pretty intimidating.
It does, doesn't it?
It kind of does, but don't worry, you don't have to be a math whiz to follow along.
Right. We're going to break down the basics, and we're going to keep things pretty light and fun.
I think it's especially useful for our listeners who are high school math teachers.
Oh, absolutely.
Because even if you don't teach abstract algebra directly, a lot of the concepts we're going to talk about, they actually underpin other areas of math.
Exactly. Things like calculus, discrete math, coding, you name it.
So this is almost like a deep dive into the deep dive,
I like that.
looking at the foundations of the foundations.
Perfect.
We're using Contemporary Abstract Algebra as our guide.
Great book.
And we're going to focus on the first few chapters. Chapter 0, Preliminaries, Chapter 1, Introduction to Groups, Chapter 2, Just Groups, and Chapter 3, Finite Groups, Subgroups.
That's a great place to start. Those chapters lay the groundwork for everything else.
We're not going to get bogged down in all the, really technical proofs or anything.
No, we'll keep it conceptual.
Yeah, we'll focus on the big ideas and how they all fit together.
And how they relate to what you're already teaching.
So let's jump right in with Chapter Preliminaries. This chapter really sets the stage, right?
It does. It starts with some basic properties of integers. One of the first things it talks about is the well-ordering principle. Now, this principle says that every non-empty set of positive integers has a smallest element.
Okay, so any set of positive whole numbers, you can always find a smallest one.
Exactly. It might seem obvious,
Yeah?
but it's actually really important for proving things in math. Like, if you're trying to show that a certain equation has a solution, you can use the well-ordered principle to say, hey, there has to be a smallest solution.
That makes sense.
And it also comes in handy for proofs by induction, something your students might come across.
Oh, right, yeah.
Then the chapter moves on to the division algorithm.
Which I'm guessing has something to do with division.
It does. Basically, it says that if you divide an integer, let's call it a, by another positive integer, b, you'll always get a unique quotient q and a unique remainder r, which is smaller than b. It's kind of like what you learned in elementary school.
Like 17 divided by 5 is 3 with a remainder of 2.
Exactly. 17 equals 5 times 3 plus 2. That's the division algorithm in action.
I remember doing a lot of those problems back in the day. I see how it connects to what we teach.
And this seemingly simple idea actually leads to some really cool concepts, like the greatest common divisor, or GCD.
The GCD.
Yeah, it's the biggest number that divides two other numbers without leaving a remainder.
Right, right. So like the GCD of 12 and 18 is 6.
Exactly. And it's not just about simplifying fractions. The GCD has applications in number theory and even cryptography. And one of the ways to find the GCD is by using something called the Euclidean algorithm.
Okay, that sounds a bit more complicated.
It's not really. It just uses the division algorithm over and over again. Like if you want to find the GCD of, say, 28 and 20.
28, 20, okay.
First, you divide 28 by 20, and you get a remainder of 8. Then you divide 20 by 8, and you get a remainder of 4. Finally, you divide 8 by 4, and you get a remainder of 0. So the last non-zero remainder, which is 4, that's your GCD.
So you just keep dividing until you hit 0.
Pretty much.
So we're building these ideas, right? We start with well ordering, move to the division algorithm, then GCD, and the Euclidean algorithm kind of ties them all together.
You got it. And then there's Bezout's theorem, which tells us something pretty cool about the GCD. It says that if D is the GCD of two integers, a and b, you can always find two other integers, let's call them x and y, such that a times x plus b times y equals d.
So you're saying that the GCD can always be expressed as a combination of the original two numbers?
Exactly. It's a bit like a puzzle where you're trying to find the right combination to get the GCD. And this theorem is really useful in number theory, especially when you're trying to find solutions to certain kinds of equations. Like in our 28 and 20 example, the GCD was 4. You can express 4 as 28 times 3 plus 20 times negative 4. So 3 and negative 4 would be our x and y in this case.
It almost seems like magic. You can find those numbers.
You can. There are ways to calculate them. It's pretty neat.
I love how all these ideas are connected.
That's one of the cool things about math.
The chapter also talks about prime numbers. I feel like most people have at least heard of prime numbers.
Well, for sure. Prime numbers are those numbers greater than 1 that are only divisible by 1 in themselves, like 2, 3, 5, 7, and so on.
Yeah, and they're really important because they're kind of like the building blocks of all the other numbers.
Exactly. And that brings us to the fundamental theorem of arithmetic, which states that any integer greater than 1 can be written as a product of prime numbers in only one way. You might rearrange the primes, but you'll always end up with the same set of primes.
Okay, so like 12 is 2 times 2 times 3, and that's the only way to write 12 as a product of primes.
Precisely. And it doesn't matter how you get there. You can start by dividing by 2 or by 3, but you'll always end up with those same primes.
So that theorem guarantees that there's only one prime factorization for each number.
That's right. It's a pretty powerful idea.
So we've covered some key properties of integers. Now, what about modular arithmetic? That's something I always found a little tricky.
Modular arithmetic is all about remainders.
Okay.
Imagine a clock.
I have one right here.
Perfect. What happens when you go past 12 o'clock?
You start over at 1.
Exactly. That's modular arithmetic in action. You're essentially working with a finite set of numbers
Yeah.
you wrap around when you reach the end.
I see. So modular arithmetic is like clock arithmetic.
Exactly. We say two numbers are congruent modulo a certain number, let's say n, if they have the same remainder when you divide them by n.
So like 15 is congruent to 3 modulo 12 because they both have a remainder of 3 when divided by 12?
You got it. And the cool thing is that you can do arithmetic, addition, subtraction, multiplication with these congruences, and it all works out nicely.
So you're saying that modular arithmetic is more than just clock arithmetic. It has its own set of rules.
Exactly. It has its own set of rules, and it's a really powerful tool in number theory and other areas of math. It actually has tons of applications in computer science and cryptography.
So it's not just theoretical.
Not at all. It's very practical.
Okay, so modular arithmetic, I'm starting to wrap my head around it.
Good. Now, another important concept from the preliminaries chapter is equivalence relations.
Equivalence relations.
Yeah. Imagine you have a set of objects, and you want to group them together based on some shared characteristic. That's where equivalence relations come in.
Okay, so you're basically creating categories within a set.
Precisely. And an equivalence relation has to satisfy three properties.
Yeah.
First, it has to be reflexive, meaning every object is related to itself.
That makes sense. Like a triangle is similar to itself.
Right. Second, it has to be symmetric. So if object A is related to object B, then object B has to be related to object A.
Like if triangle A is similar to triangle B, then triangle B is also similar to triangle A.
Perfect example. And finally, it has to be transitive. So if A is related to B and B is related to C, then A has to be related to C.
So if triangle A is similar to triangle B and triangle B is similar to triangle C, then triangle A has to be similar to triangle C.
Exactly. And when you have an equivalence relation, it partitions the set into these distinct subsets called equivalence classes.
So each equivalence class contains objects that are all related to each other.
That's right. And a good example of this is, again, congruence modulo a number. If you take the set of integers and define an equivalence relation where two integers are related if they have the same remainder when divided by 4, then you get 4 equivalence classes.
So multiples of 4.
Yes. Numbers that leave a remainder of 1 when divided by 4.
Those that leave a remainder of 2.
And those that leave a remainder of 3.
And no integer can be in more than one of these classes.
Exactly. It partitions the integers into those 4 distinct categories.
Equivalence relations, they seem pretty abstract.
They are, but they're super useful in all areas of math. They help us organize and understand complex structures.
Makes sense. So are we done with the preliminaries chapter?
Almost. There's one last thing, a quick review of functions.
Functions. Those are a bit more familiar.
They are. But it's always good to review the basics. Remember, a function is a rule that assigns each element in one set, called the domain, to exactly one element in another set, called the codomain.
Right.
And we have different types of functions. Injective functions, also known as one-to-one functions, where every element in the domain maps to a different element in the codomain.
So no two inputs can have the same output.
Exactly. Then there are surjective functions, also called onto functions, where every element in the codomain is hit by at least one element in the domain.
So every possible output is achieved.
Precisely. And then there are bijective functions, which are both injective and surjective.
So they're like the perfect matchmakers, pairing every element in the domain with a unique element in the codomain and vice versa.
Exactly. And because of that perfect pairing, they have an inverse function. A simple example is the function fx equals x plus 1, where the domain and codomain are both the set of all integers. It's projective because for any integer, you can find a unique integer that maps to it.
So that wraps up chapter 0.
It does. We covered a lot of ground, from the well-ordering principle to the division algorithm, GCDs, prime factorization, modular arithmetic, equivalence relations, and functions. It's a lot to take in.
It is, but it's all really important for what comes next.
Absolutely. These concepts form the foundation for understanding groups, which is what we'll tackle in Chapter 1.
Okay, bring on the groups.
All right, so Chapter 1. Introduction to groups. It kicks off with a really interesting example to introduce this idea of a group, the symmetries of a square.
Symmetries of a square.
Yeah. Imagine a square. What are all the ways you can move it around so that it ends up looking exactly the same?
You can rotate it.
Right. You can rotate it 90 degrees, 180 degrees, 270 degrees, or 360 degrees, which is the same as not rotating it at all.
And you can flip it like a mirror image.
Yes. You could flip it horizontally, vertically, or across either diagonal.
So there are a total of 8 symmetries.
Precisely. 4 rotations and 4 reflections. And this set of 8 symmetries, along with the operation of combining symmetries, forms what we call a group. It's called the dihedral group of order 8, and is often denoted as dA.
Okay. So what makes this a group? What's so special about these symmetries and how they combine?
Well, a group has to satisfy 4 properties.
I'm all ears.
The first property is closure. That means if you combine any 2 symmetries in the group, the result will always be another symmetry in the group. Like, if you rotate the square 90 degrees and then flip it horizontally, you end up with a new position that's equivalent to one of the other 8 symmetries.
Okay, so the group is self-contained.
Right. The second property is associativity. That means if you're combining 3 or more symmetries, it doesn't matter how you group them. The end result will be the same. Think of it like putting on your socks and shoes. It doesn't matter if you put on your left sock and then your right sock and then your left shoe and then your right shoe, or if you do left sock, left shoe, right sock, right shoe. You end up with the same result.
That's a good analogy.
The third property is the existence of an identity element.
And that would be?
That would be the symmetry that does nothing. In this case, it's the 0-degree rotation.
So it's like adding 0 or multiplying by 1. It doesn't change anything.
Exactly. And the fourth property is the existence of inverses. For every symmetry, there's another symmetry that undoes it, taking you back to the starting position.
So like if you rotate the square 90 degrees clockwise, the inverse would be rotating it 90 degrees counterclockwise.
Exactly. And if you flip it horizontally, the inverse is just flipping it horizontally again. You're back where you started.
Okay, I'm starting to get a feel for these group properties.
Great. Now, one thing that might surprise you is that with these symmetries, the order in which you combine them matters.
So it's not like regular addition or multiplication where a plus b is the same as b plus a.
Exactly. With the symmetries of a square, if you do a horizontal flip and then a diagonal flip, you'll likely end up with a different result than if you do the diagonal flip first and then the horizontal flip.
So the operation is not commutative.
We got it. We say that D is a non-abelian group because the order of operations matters.
Non-abelian. Yeah, I'll try to remember that.
And that brings us to the formal definition of a group. A group is a set, along with an operation, that satisfies those 4 properties we just talked about: closure, associativity, identity element, and inverses.
And the symmetries of a square are just one example.
Exactly. The power of abstract algebra is that this definition applies to all sorts of different sets and operations. The chapter goes on to give several other examples, like the integers under addition.
Okay, so like 2 plus 3 is 5, which is another integer.
Right. And addition is associative, 0 is the identity element, and every integer has an inverse.
Monomer 2 is the inverse of 2, and so on.
Exactly. And because addition of integers is commutative, meaning a plus b is always the same as d plus a, we say that the integers under addition form an abelian group.
Abelian, the opposite of non-abelian.
You got it. Another example is the set of non-zero rational numbers under multiplication.
So fractions.
Yeah, fractions where the numerator and denominator are integers and the denominator is not 0.
Okay.
Multiplication is associative, 1 is the identity element, and every non-zero rational number has an inverse.
Like the inverse of 23 is 32.
Precisely. And this group is also abelian because the order of multiplication doesn't matter.
So we have abelian and non-abelian groups. What other distinctions are there?
Well, there are finite groups and infinite groups. A finite group has a limited number of elements. Like d euro, the symmetries of a square, only has 8 elements.
And an infinite group has an unlimited number of elements.
Exactly. The integers under addition form an infinite group.
Okay, that makes sense.
And then there are cyclic groups, which are groups that can be generated by a single element.
Meaning
you can get every element in the group by starting with one particular element and repeatedly applying the group operation. The integers modulo n under addition are a good example of cyclic groups. You just keep adding 1 modulo n, and you'll generate all the elements in the group.
So those are some of the different types of groups.
Exactly. And there are many others, but those are some of the key ones to get started with.
Okay, so that's Chapter 1, Introduction to Groups. A lot of new terminology, but I'm starting to see the bigger picture.
Good. It takes some time to get used to all the abstractness, but once you do, it's really quite beautiful.
So what's next? Chapter 2.
Yes. Chapter 2, Just Groups, dives deeper into the structure of groups. One of the first things it explores is the concept of subgroups.
Subgroups.
It's pretty much what it sounds like. A subgroup is a subset of a group that itself forms a group under the same operation. It's like having a smaller group nestled inside a bigger one.
Okay, so you're looking for sets within the group that still follow all the group rules.
Exactly. And there's a handy test to determine if a subset is a subgroup, called, appropriately, the subgroup test. It says that if you have a non-empty subset of a group, and you combine any two elements in that subset, along with the inverse of one of them, and the result is still in that subset, then that subset is a subgroup.
That sounds a bit convoluted.
Let's think about the integers under addition again. You take the subset of all even integers. You add any two even numbers. You get another even number. And if you subtract an even number from another even number, you still get an even number. So that subset passes the test and is indeed a subgroup.
Okay, so the even integers are a subgroup of all integers.
Precisely. Subgroups are super useful because they often have special properties that can help us understand the larger group.
Makes sense. What else does Chapter 2 cover?
It talks about cyclic groups, which we touched on earlier.
The ones that can be generated by a single element.
That's right. The chapter delves a little deeper into their properties and gives some more examples. It also introduces the concept of the order of an element.
The order of an element. What's that?
The order of an element is the smallest number of times you have to combine that element with itself to get the identity element.
Okay.
Like in the group of integers modulo 6 under addition, the element 2 has order 3. Because if you add 2 to itself 3 times, you get 6, which is congruent to 0 modulo 6, which is the identity element.
Ah, okay, so it's like how many times you have to apply the operation until you're back to neutral?
Precisely. And if you can't get back to the identity element by repeatedly combining the element with itself, then we say the element has infinite order.
Makes sense.
And finally, Chapter 2 gives us a sneak peek at one of the most important theorems in group theory, Lagrange's theorem.
Ooh, a theorem. That sounds serious.
It is, but it's also really cool. It basically says that if you have a finite group, the number of elements in any subgroup has to divide evenly into the total number of elements in the group.
Okay.
Like if a group has 12 elements, you could have subgroups with 1, 2, 3, 4, 6, or 12 elements, but you couldn't have a subgroup with 5 or 7 elements.
So Lagrange's theorem puts some constraints on the possible sizes of subgroups.
Exactly. It's super helpful for understanding the structure of finite groups.
Okay, Lagrange's theorem. Got it. And that wraps up Chapter 2.
It does. We're making good progress. Chapter 3, Finite Groups, Subgroups, really focuses on, you guessed it, finite groups.
So groups that have a limited number of elements, like the symmetries of a square.
Exactly. The chapter goes into more detail about subgroups, especially in the context of finite groups.
Okay.
It talks about how understanding the subgroups of a finite group can help us classify and understand the structure of the group as a whole. And it formally states Lagrange's theorem again.
Right, the one about how the order of a subgroup has to divide the order of the group.
Precisely. It also highlights the connection between the order of an element and the cyclic subgroup that it generates. Remember, the order of an element is the smallest number of times you have to combine it with itself to get the identity element. Well, if you keep combining that element with itself, you create a cyclic subgroup. And the order of that subgroup is the same as the order of the element.
Ah, so the order of an element tells you how many elements are in the cyclic subgroup it generates.
Exactly.
Okay, I'm starting to see how these pieces fit together.
That's great. The chapter also touches on the idea that you can classify subgroups into 2 types. Cyclic subgroups, which are generated by a single element, and non-cyclic subgroups, which require more than one generator.
And it mentions that the identity element always forms its own trivial subgroup.
Yes. It's the smallest possible subgroup with just one element.
Makes sense. So we've covered a lot of ground in these first 4 chapters.
We have. We started with the preliminaries, laying the foundation with concepts like the well-ordering principle, the division algorithm, prime numbers, modular arithmetic, and equivalence relations. Then we moved into the world of groups, exploring their properties, different types of groups, and subgroups. And we learned about cyclic groups, the order of elements, and even Lagrange's theorem.
It's been a whirlwind tour, but it's also been really fascinating to see how these seemingly abstract concepts actually connect to a lot of the math that our listeners teach every day.
Absolutely. Even if you don't teach abstract algebra directly, understanding these fundamental ideas can deepen your appreciation for the structure and beauty of mathematics as a whole. And that can only benefit your students.
Absolutely. And here's something for our listeners to ponder. We've talked about the symmetries of a square, but what about the symmetries of other geometric shapes? Do they also form groups? And how might that connect to what you teach about geometric transformations?
Those are excellent questions. And another thing to consider is how modular arithmetic, which we explored in Chapter 0, actually underpins a lot of what goes on in computer science, especially in coding. It's all about working with finite sets of numbers and remainders, which is exactly what computers do.
I love those connections.
Me too. It's a reminder that even though abstract algebra might seem far removed from everyday life, it's actually all around us.
Well said. Thanks for joining us on this deep dive. I know it was a lot of information, but hopefully it was also enlightening and maybe even a little bit fun.
My pleasure. It's always fun to talk about math.
And for those of you who want to learn more, we encourage you to dive into Contemporary Abstract Algebra and explore these ideas further. Until next time.